What types of forces have you seen in physics problems before? What kind of forces? Okay, normal. So normal forces, what else?
Force of friction.
Hang on a sec. Stop. Okay, I heard friction,
Wait.
weight. So in physics, you use mass a lot. And typically you said mg all the time, right? And you represented forces as mg. Well, we're going to calculate what that mg value is, because in statics problems, we're always using weight. Scientists tend to look at mass more importantly, but in engineering, we're using forces. So we're always going to convert everything. If we're given masses, we're converting it right away to get our weight. Okay? We don't talk about the mass of each one of us, right? We talk about the weight of each one of us. Okay, normal, friction, weight, what else? Tension.
Nuclear. Magnetic. Electrical.
No, just regular physical loads like this, not electrical loads. That's your Monday, Wednesday morning class.
Monday.
Let's talk about tension. What is tension? A pull, right? When you're being pulled. It's a pull force. What's the opposite of tension?
Compression.
Compression.
Horsepower.
So if I have a body, I'm drawing over here high, is that okay? I have a body and it's on some surface, and this is how you denote a surface. And then there's some cable that runs up to a ceiling, so there's another surface.
That little hashtag thing is surface.
Yes, this means surface.
Cool.
Okay. If you had water, you would do this. You did water. Okay, so we're looking at this body and we're assuming it's homogeneous. And I want to look at this body and I want to think about, okay, so we listed some of the forces. So how are we going to draw these forces? This right now is scrap. It's my scrap paper. I'm drawing it right on the picture that's given. It's scrap because it's not a true free body diagram when you draw it directly on. So what do I need to draw on here? You said a normal. So how is normal drawn? It's perpendicular to the surface and which direction? Towards the surface. And it's denoted by capital N, and we're going to use the variables that are typical. So it's perpendicular to the surface, but it's drawn towards the surface. So would you say it's a tension or a compression force? Try again. Tension is a pull, compression is a push.
Oh.
What is it, tension or compression?
Compression.
It's compression. This inclined surface is pushing up on this. Okay, that's normal. How about friction? Let's do friction last. Let's go to the next one. Weight. How do I draw weight? Always down. And which way? Away from the body. Always down. Some students come from physics saying, oh, the normal and the weight are equal. In this case, the normal and the weight are equal.
No.
They're not. They're in different directions, okay? On a problem like right now, my normal and my weight are equal because my weight's going down and the normal's coming up. Then if you break it up into components, then the weight, well, let's look at those other forces. If there was only normal and weight, then the normal would be a component of the weight and the weight would be a component of the normal. How about tension? Do we have a tension in here?
Yes.
Yeah, we have it in the cable. And it's in along the direction of the cable, and how is it drawn? Towards or away?
Away.
Away. Tension. Let's go back to friction now that we have the others drawn. If this cable was to be cut, and let's say this was free to move, which way would it go?
Down.
Down. So which way do you draw the frictional force?
The opposite way.
Right.
Along the front.
It's parallel to the surface, and let's just call it F sub F. All these forces are vectors, right? Right? They all are vectors, so they have a magnitude, and we use variables to define them, and they had a direction. Normal is drawn perpendicular to the surface towards the object. Weight is always drawn down away from the object. Tension is drawn along the cable away from the object. Friction is drawn parallel to the surface in the opposite direction of motion. This is not a free body diagram, because right now, even though we know these forces exist, we're drawing them on the body. We have to draw them on the body isolated from the objects. When this tension, when this cable is still like that and not cut, it has an internal tension, not an external tension. Here we have our normal. I have to have some kind of angle, so I'll just put theta. Here I have my weight. And here I have my frictional force. This is a free body diagram. What you're doing is isolating the body that you're drawing the free body diagram of and drawing all the forces on it. So put your hand there. So right now, what kind of force is Sarah putting on me and I'm putting on her? A compression force, right? But right now we're in static equilibrium, right? She is feeling the force from me and I'm feeling the force from her. But it's not until I separate my body that I could actually draw her force on me. Everybody got that? This is something new, okay? You guys covered so much in Physics 4A, so much material, that they couldn't do some details. You've always drawn free body diagrams right on the parts when it's connected. It's not drawn. When it's connected, there is a normal from the surface on the body, and there's a normal from the body on the surface. You hear that? Okay. There's equal and opposite forces here. What was that, the third law? It's not until you isolate the body that you draw the forces that you're showing the free body diagram. And all these should have directions, right? Some kind of direction. I'll call it delta 1, delta 2. We have to have some kind of direction showing it. Uriah, did you have your hand up?
I was just wondering, it's okay to just represent the rock as a dot instead of drawing the rock?
Not in this case. Good question. He asked, can we just represent the rock as a dot? We can't, because take a look, this frictional force, this tension it's supposed to go through, it's supposed to be a straight line. The tension goes through the point, the weight goes through the point, the normal goes through the point, but does this guy go through the point? No, it's causing a rotational motion, right? So it's got to be right here. You have to draw the body in this case. If there was no friction, you could have isolated it only as a dot. Okay. To give you some terminology, T, N, and W are called concurrent, and this you need to know. Concurrent forces. What do you think concurrent forces means? If I said that it's T, N, and W are concurrent.
They're acting at the same time?
Acting at, not only at the same time, but acting at the same, it has to do with a location, point. They're all acting at the same point.
You said that tension, normal, and weight?
Yeah, tension, normal, and weight. Tension, normal, and the weight. So let's think about that. Everybody look up here. If I have this body and all the forces are acted towards the center of the body, what kind of motion can this experience? Well, first, what are the two different types of motion?
Linear,
Translational and
Rotational.
rotational. If all the forces are acting at the same point, what kind of motion can it experience? Translational only. It's either going to move this way, this way, this way. It's not until I put another force that's not concurrent that actually could cause it to rotate. So if there was no friction, this body is only going to move translationally, linearly.
Do we use the term moment of inertia in statics?
Moment of inertia, yeah, and we'll have a clarity of what moment of inertia is later on. The reason we use moment is because moment of inertia is actually the second moment, the second torque. You'll see.
Okay.
So that's why we use the word moment.
Just curious what letter you
It's
use.
the last topic in the class.
What letter do you use for compression?
Say it again?
Just curious what letter you use for
C.
compression. Okay.
Okay. So, do we have an agreement that we're always going to use W for weight?
Yes.
You guys good with that? Normal, N,
Yes.
T for tension?
Yes.
Good. Okay, so let's take a look at some problems. We're going to start, so now we're starting to do statics problems. Last week we just did component stuff.
So in the future, we're gonna be putting our own stuff out.
Say it again?
In the future, we're gonna put our own stuff out.
Yeah, so either you can print it out or get it at Print Smith. Yeah. I like working off the problems and writing on them when I was a student. You know, I didn't like when a teacher said, okay, everybody turn to page 20 and let's look at problem 5, 6, and then if I wrote on the textbook, then I didn't have an original problem anymore, right? So I like to work on paper, so the packet's a good idea. Okay, so let's take a look at this. When we do statics problems, these are the steps we're going to follow. You see at the top, static steps in problem solving in chapter 3. And typically what we're trying to do is find some unknown pieces of information. So the first thing we do is we always look at what's given. And the given information is presented in the drawing and in the words. Then we want to figure out what we have to find. So this is really the same steps we do when we're solving a problem as an engineer, when we're doing some design. What are we given? What do we need to find? We identify, next step 3, identify all the forces in the system. Then we're going to make a table that determines what forces, magnitude, and the directions are unknown. It may not be clear as to what this is, but we're going to work through it. Then we figure out how many unknowns we have and how many equations we need. Then we determine which body or bodies we need to draw a free body diagram of, and then we draw the free body diagram. So all this, step 1 to 7, is the setup. And then this is the number crunching. It's called crunching. Okay? So what we're going to do is we're going to set up a bunch of problems first before we start doing number crunching. So steps 1 to 7. Okay, so, you know, on the back of the sheet, we're going to look at these on the back of the sheet a little bit. Okay? These are the full problems we're going to do. We're just going to do some setup now. Okay? And this is in your packet. It's on page 11. So what's the first step? What's given, right? So right, given. Take a look at the picture first. So we have a cylinder, it's leaning on the surface, it's at a 55 degrees, there's a cable there, 75 degrees. I mean, I think you guys would probably agree with me, I hate reading words. I'm not sure how to look at just the picture, but we gotta read them. Homogeneous cylinder, that's important, right? Why do we want to know it's homogeneous?
Equal density.
We know its weight is in the middle, right? It weighs 500 pounds. Well, good thing I read it, because I wouldn't have known that was 500 pounds. And I'm going to look this up, do scrap here. so I know 500 pounds. It's supported by a flexible cable. What does that mean? If something is flexible, if I have a cable that's flexible, what kind of load can it take?
Tension
It
only.
can still take tension. Can it take compression?
No.
No. How about if it was stiff? How about if it was a rod? Can it take tension?
Yes.
Can a rod take compression?
Yes.
Yes. So when they say flexible cable, it's just telling us it can't take compression, it's only tension. So I'm going to put a T here. Again, it's all scrap. Smooth inclined plane. Why is it telling us it's smooth?
Frictionless.
Hmm?
Frictionless.
No friction. And actually, we're not dealing with friction until we get to like chapter 8 or 9. So everything's frictionless to begin with. So frictionless, no friction. Determine the tension T in the cable and the force R exerted by the inclined plane. Well, what are they talking about? Force R exerted by the inclined plane on the cylinder. They really mean the normal. Let's teach them that we're not using R, we're using N. So where does N get drawn? Well, N gets drawn like this, right? Perpendicular towards the cylinder. So what is given? Well, the weight. And when I say given, so let's go back to this. Given. Anything not given in the sketch or the schematic. Because it's easy for me to look back at the picture, right? But I don't really want to look back at the words. Once I read it once, I don't really want to look back at it again. So my given information is the stuff that I learned from here. So 500 pounds. Everything else is in the picture. How about find? What do they want us to find? They want us to find the tension, and they want us to find the normal. So far I just did step 1 and 2, given and find. And now I'm going to draw a table. The table, the first column of the table is the force. The next column is magnitude, and the next column is direction. So do you agree that all forces are vectors?
Yes.
So they have a magnitude and a direction. So let's see. So what I'm going to do, and I do this in my classes, I just kind of go around. I'm just going to go around, and you can pass if you don't want to answer. So Rachel, could you give me a force that's given? A force in the system, the weight. Is the magnitude of the force given to us? Yeah. Is the direction of the force given to us? Yeah, we know it's down. So we know everything we need to know about the weight. Chris, how about give me another force that's in the system?
The normal?
The normal. Do we know the magnitude of the normal?
No.
No. Question mark. Do we know the direction of the normal?
Yes.
Yeah. So the normal is giving us one unknown so far, right? We know the direction of it, but we don't know the magnitude of it. Sarah?
Tension?
Tension. Do we know the magnitude?
No.
Do we know the direction?
Yes.
Yes. Lonnie, any other forces in the system? No, that's it. So, how many unknowns do I have? Two unknowns. Two unknowns. So Claire, if I have two unknowns, if I want to solve this problem, how many equations do I need?
2.
Two equations. So if I have a two-dimensional body, so Nicholas, how many equations can I get from that body? And what are they? If I want to do static equilibrium equations on 2D, just take it out. Two equations and tell me what they are. If it's not moving, right? If it's not moving, and this is the x direction and this is the y direction, couldn't I say the sum of the forces
The axis is
and the x equals 0, and the sum of the forces in the y equals 0. Does everybody agree? So for each body that I analyze, I have two equations. How about if it's a 3D body? 3. What are they?
Those two, and then some of the forces in the Z.
Some of the forces in the x equals 0, some of the forces in the y equals 0, and some of the forces in the z equals 0. Some of the forces in the z equals 0. So I have 3 equations here, and here I have 2 equations. And this is per body. So if it was a 2-dimensional problem, and I was analyzing 3 different bodies, how many equations do I have? 6. 3D problem, 2 bodies, how many equations do I have total? 6. 2 bodies, 3D, 3 times 2, 6. So this is 3 equations per body, 2 equations per body. And right now, we're only dealing with concurrent forces. What's concurrent forces?
Forces acting at the same point.
All acting at the same point. Acting at same point. That means there's no possibility that it's going to rotate, right? So I can't do sum of the torques equals 0 yet. I have to wait. Right now, the forces are only concurrent, so I only have force equations. So let's go back to this. So Chelsea, we found analyzing this problem that we have 2 unknowns. And since we have 2 unknowns, we need 2 equations. How many bodies do I need to analyze? Let's see. This is a 2D problem, right? And if we go back over there, we know that we have 2 equations for each body. And I need 2 equations, so how many bodies do I need to analyze? 4? No, let's try it again. Yeah. So for each body, I could get some of the forces in the x and some of the forces in the y, right? So one body, I could do some of the forces in the x equals 0, some of the forces in the y equals 0. So that's giving me 2 equations. And I need 2 equations. I only have to do one body. Okay? And Nick, what body do you want to analyze?
We're looking at the steel cylinder.
The cylinder. So in this case, I can't remember who asked me the question. I think it was Aaron. No, Uriah. In this case, these are all concurrent forces, right? So do I have to draw it as a cylinder, or could I draw it as a dot? Dot. So here's my free body diagram. So what do I need to put in a free body diagram? I need to have an x and y, z, x, y, and z if it's 3D axes. So I'm drawing the axes first. Then I'm going to draw my normal. I'm going to draw my tension. And I'm going to draw my weight. So Janae, what's missing from this free body diagram? I drew my axes, I drew the forces, but what am I not telling you about the forces? The angles, I'm not giving you the direction of them. So I need to do that. So let's take a look at the tension. Well, I'm going back to my scrap. If this is 75 here, then that means this is 75. The weight is fine, and I know it's 500, so I'm going to write 500, so I don't think it's an unknown. And now I'm going to give you a trick. So they have the inclined surface. This is something you would have learned in geometry way back. And they're saying this is 55 degrees. And my normal is like this, right? And I can draw it up. Remember, I don't have to stay down here. But I need to figure out what this angle is here. So I'm going to draw, let's do it with a different color. This is my y, Okay. This normal force is perpendicular to the surface, right? Everybody up here? This is perpendicular to the inclined surface. What's perpendicular to this, the horizontal? Which axis? Y. Y is perpendicular to the horizontal surface. The angle between the horizontal surface and the inclined surface is 55 degrees. That means that the angle between two lines that are perpendicular to each one of these is 55 too. So what's perpendicular to this? The y-axis. What's perpendicular to this? The normal. This right here is 55 degrees.